back to that list of problems here and go to number 2, where here we have this same case, where now we have a cube being submerged here, suspended in this case by a scale. So let's just imagine this like our little spring scales we've been using in lab, where you've got your readings on here in newtons, and you're holding that, submerging that, or suspending this mass, holding it there inside of a container of fluid. Okay, you get a steel cube here, 0.3 meters on a side. So let's say the volume of that cube is equal to 0.3 meters cubed to find the volume. We know it's steel, so we can look up the density of steel, which is 7,800 kilograms per cubic meter. All those numbers in your table in the book are all written in scientific notation with powers of 10 to the third attached to those. You can write it with 10 to the third or write like this, doesn't matter, but just make sure you notice those 10s that are there when you're using that table. So we're suspending the steel cube in water. So if it's water, we know the density of, I'm just going to put the F here for the fluid. The density of the fluid will be 1,000 kilograms per cubic meter. You can put W for water, you can put the whole word for steel, but pick a convenient single subscript sometimes, because when you put these into the equation, it just saves you writing and having to actually write out steel or H2 or anything like that. We want to know what the scale is going to read. If this cube here had a weight of 1 Newton, when I'm just holding it here, will that scale reading be bigger or smaller than 1 Newton when I put it in the water? Quite smaller. The buoyant force is helping to push it up. Have you all tried to lift something in water before? An anchor out of a boat? Maybe a kid. Have you ever taken your kids and thrown them up in the pool? Or a friend or something? Have you done that? I don't know if you use kids, but you have fun with your nephews or something. But I mean, go home and take your kid and give them a throw if you want to. But, or lift anything in the water. Pick up a weight, pick up an anchor, pick up something. You probably all felt that effect. Maybe you haven't realized it. But when you're lifting it in the water, it's going to be different than what you feel when you pull it out of the water. Okay. So when it's in the water, apparently it's going to look like it weighs less on our scale here. So we should expect a number that's smaller than whatever it would be. We haven't found what that weight is here yet, but that's what you should be expecting here for the scale reading. Okay. What should I do next? How should I approach this? What does the scale read? What units? Grams or kilograms in our lab scale, but then we always convert that to what? A force, right? What do we do when we're solving force problems? Always. If you're talking about buoyancy and there's forces involved, you just start with the free body diagram. Okay. This is no different than what we've done before. We have one new force now of the fluid acting on this mass here. Everything else is the same. We have contact forces, we have gravity, and now we have this new contact force from the fluid here. But there are no other forces that we know about. It's the same as always. Let's just look at the mass, draw all the contact forces that are acting on it, get your weight force in there. So I'll put the weight force in here now. Call that W, going down like that. Okay. What else do we have? The normal force from the scale. It is normal because it's perpendicular, but it's not like a push contact kind of normal force. Let's just call it here. This could be if it was a string or the spring that's attached to it. It could be a tension force. I'm just going to call this the force of the scale right now. Okay. So let's just call this, because that's what we're looking for. Let's just call this the force of the scale. I'm just going to write the whole word there so we see it there for the first time. We also have the buoyancy force, which goes which way? Up. Always up. Draw the buoyant force here. Label it as FB. I'm not worried right now about the relative lengths of these two compared to each other, how they compare. I just know they're both going up. What else is touching it? water. We have that, right? And the water's touching it on all sides, but that's all in right here. Okay? The water, the scale, that's it, right? And gravity. Same as before. Make sure you account for all your contact forces, only things that are touching it, and then the gravitational force here. Draw your free body diagram, choose your coordinate system. And then what do we do after this? Sum of the forces. Use Newton's second law, sum of the forces equals ma. We're going to do the y direction here. Fortunately for you, I don't give you any problems where the forces are not strictly vertical. Okay. I could definitely have a rope here. I could be kind of pulling something across the water or something. We're not going to have accelerations. We're not going to have horizontal forces here. These are going to be vertical forces here. They could be other forces. We could definitely have other things in here, but the ones that we're doing just don't have those. These will all be just vertical forces. And the A is going to be 0 all the time here. But I'm still going to start off by writing it that way, just like we always do. Free body diagram, your coordinate system, and then set up this equation. FB plus the force of the scale minus the weight is equal to 0. Okay? So you're definitely going to need your free body diagram for this final exam for buoyancy. The one place where I told you with the comprehensive material that I might ask you to write out an equation will be things like this. I'll probably give you 1 or 2 of those problems with the free body diagrams, like the little boxes I gave you, and have you complete those like we've done before. But it won't be solving the whole equation, it'll just be setting them up where I want to see you can still draw a free body diagram. You might have to use sines and cosines for drawing some components, but for all the older material, I've told you before that you're not really solving any problems. The free body diagram is probably the most actual writing you'll have to do for those in terms of equations or anything. There may be a short answer or a sentence or two sometimes, but that's one more thing that you'll have to be able to do in addition to just a free body diagram for your buoyant forces here. Okay. What are we solving for here? What does the scale read? That's this force right here. Let's just solve the equation. Once you get down to here, this should feel very familiar. These are just forces now. Now these are different things that we have from before, but this line here is something we've done quite often. This is just mg minus the buoyant force. Okay. But this is where we learned what the new buoyant force is. Put that in. Now which mg is that? Is that the mass of the water? Is that the mass of the cube? That's the mass of the cube. So let me just go ahead and call this, for now, the mass of steel times gravity, because that was just the weight force. This was the free body diagram for the cube. That is just the true weight of the cube, which is just the mass of that steel times gravity. We don't know what that is, but we do know it's the mass of that cube. How would I write the buoyant force?
P,
Density, yeah, rho of the fluid times gravity times the volume. And you could write rho Vg if you want to. The order doesn't matter there and how you write those things out. But that's the density of the fluid times gravity times the volume of the fluid displaced. Okay. In terms of our notation that we started off with over here, the S's, the F's, the V, what would this V right here be?
Volume of the cube.
That's just the volume of the cube. It's the volume of the fluid displaced, but this whole cube is in the water, so the volume of the fluid displaced in this case is the same as the volume of the cube itself. So this is Vf is equal to V here because the cube is completely submerged. So we know that. Now the mass of the steel, do we know that?
Use density to find it.
So we can say this is the density of the steel times which volume?
the
Volume
volume,
of
the same volume.
The same V times G. And what if that cube was up like this on the scale? If I was doing the mg, which volume would I use if it was this case? you would still use the whole volume. When you're finding the weight of the object, it doesn't matter whether it's completely submerged or not. Its weight is its weight, based on its mass. Okay? It's this term that depends on how much is in the fluid or not. But the mg term is always based on the total volume of the object, whether it's completely submerged or not. Okay? So even if it was that case, that would still be the V here. That we could have put an S on here if you wanted the volume of the steel, but I just chose to label this as the volume V for the entire cube there. So at the beginning of these problems, try to slow down and give yourself some notation over here with subscripts, because you can see right here, now if I write this out, I've got rho VG minus rho VG here again, and if I don't have subscripts here, it might look like this minus this is 0. You're not keeping track of all the different subscripts here for all these terms. Okay. Now, I'll take off the F now because we said they were the same volume. And the order here doesn't matter, you know, this one has the G at the end, this one has the G in the middle, but order's all fine there. You can mix that up if you want to. Is that clear though on all the subscripts there? This is the place where I'm talking about that people get mixed up, because you start seeing rhos and V's and G's, and if you don't include the things here, and just don't know which one is which, that's where mistakes can happen. This part up here should be fairly easy, because it's just one new force up here with the buoyant force. Okay? So I think we're all good here, right? This was just the density of steel times the volume to give you the mass of that steel cube. This was the volume of the fluid displaced, which was the whole volume of the cube. That is the fluid there, so we're good with all our notation here. In terms of plugging this in, we can factor some things out if we want to save some time. The G and the V are the same in both, so it's just the density of steel times, or minus the density of the fluid left over there on the inside of those parentheses. I chose to write out the word scale this whole time through. You could have put scale here with an S, but then you might have confused that with steel. So it didn't take that much more time to keep the whole word here, but sometimes you might just choose to pick something more convenient than having to write out the whole word. But just be very clear with your notation starting over here at the beginning of the problem when you choose your subscripts. Okay? And I think we know all these things, right? Or, yeah, we didn't get a number yet, but we know this is 0.3 cubic meters, or 0.3 meters, that whole thing cubed here. The density of the steel is at 7,800, minus the density of water, which is 1,000 here. And now you can figure out what that force is in newtons here. Yeah.
I'm confused how you made the leap on, from the mass of the steel times the gravity, the second line underneath it.
To this one?
Yeah, I'm confused how you got it.
Because the density is in general mass over volume. So if we wanted the mass of that steel cube, then that mass would be equal to density times volume, and we do rho times V here to get the mass. That's where this came from, because this term right here, this is just the mass of the cube. The density of that cube times the volume gives you the mass. And we could have, in this problem, solve for that separately, because we know the volume, we could get a number for this once we multiply that or cube that. We know its density here. We could have got that number separately and just left it as mg. And then you might not have seen the same rho and v and g in the equation here. I'm writing it out this way because there are times where you'll have to, where you might not have these numbers. And just to show you that anytime we see these masses, we can rewrite those as density times volume. That's a good thing to be able to do here. But in this case, if it's easier, you really can sometimes get that mass separately if you want to. It just won't always work out that way. So get comfortable kind of looking at your equation, where you really might have rhos and v's and g's in there that are all different, and try to be able to keep track of which one is which and why there are s's here or f's there for that one. Okay? You're welcome. Any other questions?